Hey everybody, we are going to be going over the 3 different examples from the pressure, volume, and temperature relationship problems that I suggested you go over. So if you just want to check the answers, you can kind of fast forward to the answer part, or you can watch through as we go along. So a gas sample at constant pressure occupies 3.6 liters of volume when the temperature is 21.6 degrees Celsius for problem number 1. The sample was cooled and decreased in size to 3.45 liters. Determine the temperature the sample must be at when the volume is 3.45 liters. So, like I said, the law that we're kind of working with is the combined gas law. That's the one that they're going to give you. P1 V1 over T1 equals P2 V2 over T2. So you've got these as your variables in your problem. Now, again, if they start to talk about different amounts of gas or moles of gas, we got to use a different law. But right now, this is the one we're going to work with. So what I really recommend with these problems is going through, reading the problems, and figuring out your variables in your problem. So to read this, we've got our gas, volume, and temperature for our first problem. So I'm just going to literally make a list. So I've got a P1. Oops, I don't have a P1. What am I talking about here? I have a V1, and it's 3.62 liters. And I have a T1 that is 21.6 degrees Celsius. And if I keep reading, I don't have any pressure information at all, so I really whiffed that one. Sample was cooled and decreased in size to 3.4 liters. So I've got a V2 here because that's my second one, and that's going to be 3.45 liters, and it's asking me to figure out the new temperature that this volume happened at. So I don't know what that is. Now, in this case, I'm given no information about pressure whatsoever. So this law here, now what I got to do is take out the stuff that's not relevant. So I'm going to ignore the P because there's nothing here, and now I've got a Charles law problem, which again, you don't need to know the name of, but you need to know how to do this math. So if I ignore the pressure component of this, I have V1 over T1 equals V2 over T2. And it's up to you if you want to put the numbers in right away or if you want to leave them out. I personally like to solve for the variables first and then I put the numbers in. So I'm looking for T2 here. And normally I am not a big proponent of cross multiplication and division, but this is honestly the perfect example. So I'm going to cross multiply and then I'm going to divide these out. So V1 times T2 equals T1 times V2. And I want to solve for T2. So I'm going to divide both sides by V1. So what I get is an equation where T2 is equal to T1 times V2 over V1. Now, I personally do not need you to show me this mathematical rearrangement here, but what I'll do next is I'll put these numbers in. So if I have T1, that's 21.6 degrees Celsius. Now, we've got a problem here. We have to turn all of these temperatures to Kelvin to make them work with the gas laws. So 21.6 degrees. In Kelvin, I'm going to add 273, and it's going to become 294.6 Kelvin. Okay? You've got to have it in Kelvin, otherwise this does not work. So I have T1 as 294.6 Kelvin times V2, which was 3.45 liters, divided by my V1, which is 3.62 liters. Units of liters cancel out. I'm going to put that into my calculator. I get a value of 280.77 Kelvin. Now, the reason why we have to put that temperature in Kelvin is because a magnitude of a temperature change isn't necessarily going to be properly reflected by the Celsius scale. The Kelvin scale never goes negative, so it gives us a sense of the absolute temperature change that's happening there. If your problem isn't specific, you can leave it in Kelvin. Otherwise, if you want to go back to Celsius, you'd subtract 273 and my temperature would be 7.7 degrees Celsius. So it's up to you. If it asks you for Celsius, you got to do the work. Otherwise, you don't have to. In terms of what I want to see, I need to see this rearranged math and your final answer. If you put your numbers in here right away, so let's say you put in 3.62 liters over 294.6 Kelvin, and then it's equal to 3.545 liters over T2, and then you give me this, and then you give me the answer without showing me this work in the box, I am not going to give you credit. And the reason for that is because you could literally have just copied this from someone and done that. Now, is it true you could copy this? Yes, absolutely. But you need to show me the rearranged work. You don't even need to show me this. You just need to show me the rearranged equation as well as the answers. Okay? I will not be generous with that at all. Now, question 2 was a question about a syringe. You had a syringe that had a volume of 4 milliliters of gas, and then it said the pressure is decreased by half. And it didn't tell you what the pressures were, it just tells you it's going down. So in this problem, I have a volume, and I have two kind of pressures. In this case, if they don't give you any pressures, I just pick a pressure if I want to actually do the math. And if you can do this without doing the math, that's great, but I like to do the math to confirm. So I'm just going to pick an easy pressure for my first pressure of 1 atm, and then half of that is just half an atm, and that's going to make my life easy. So if you think about the law, I've got P1 times V1 over T1 equals P2 times V2 over T2. Okay? In this case, there's no mention at all about temperature. So my law is just going to be P1 times V1 equals P2 times V2. If I make my variable list, P1 is going to be 1 atmosphere. And again, you can pick anything, but I just do 1 because it's easier. V1 is going to be 4 milliliters. P2 is half of an atmosphere. And then V2 is going to be what we're solving for. Okay. Now, again, if you can do this and explain it without doing the math, that's fine, but I want to show you the math as well. So I'm going to do my algebra. P1 V1 equals P2 V2. Solving for V2. So I need to get the P2 on the other side. So V2 is equal to P1 V1 over P2. Okay. So I'm going to put that into my equation with all of my variables now. We call it plug and chug. You take these numbers, you plug them into the equation, and you chug out an answer. So P1 is 1 atmosphere. V1 is 4 milliliters. And then P2 is 0.5 atmospheres. Now, if you think about what's happening in the syringe and our relationships, the pressure is going down, so the volume should go up in this situation. And if we look at our math here, the math supports that. I have 1 atmosphere over or divided by 0.5. So if you think about it, my pressure is going down by half, but my volume is actually going to go up by a factor of 2 because 1 divided by 0.5 is 2. So in this case, atmospheres cancel out, and I end up getting 8 milliliters. The syringe that makes the most sense in this case is going to be syringe B because it's 8 milliliters. So if my pressure goes down by half, my volume goes up by a factor of 2 and vice versa. Okay. Now, the last one is probably the nastiest one of all of these. You have a 6.35 liter sample of carbon monoxide collected at 55 degrees Celsius and 0.892 atmospheres. What volume will the gas occupy at 1.05 atmospheres and 20 degrees Celsius? So if I read through this problem and I make a list of what I have here, I have a V1 to start off with, which is 6.35 liters. It's telling me it's at 55 degrees Celsius. T1, and let's just convert that to Kelvin right away. So that is going to be 328 Kelvin when we add the 273. And, oh, we got a P here too. P1 is going to be 0.892 atmospheres. Okay, keep reading through. What volume will the gas occupy? So I do not know my V2. Pressure is going to be, for the second set of conditions, 1.05 atmospheres, and my T2 is going to be 20.0 degrees Celsius, which is going to be 293 Kelvin. So I've got a lot of information here, which means we're probably going to be doing all the math. if you think about what's happening, sometimes it's easy to predict what's going on. So in this case, the temperature is going down and the pressure is going up. So if you think about our relationships, as T goes down, the V is going to go down. And as P goes up, V goes down. So if we do this right, our volume should be less than 6.35. So let's do some algebra. P1 V1 over T1 equals P2 V2 over T2. We are solving for V2. So we're going to cross multiply and divide to get our variables all figured out. So we've got P1 V1 T2 equals P2 V2 T1. Lots of letters and numbers here. I'm solving for V2. So I'm going to solve both sides by dividing by P2 T1 and P2 T1. So you can see this has the potential to get kind of nasty if you aren't paying attention. So at the end here, V2 is going to be equal to P1 V1 T2 divided by P2 T. See, I can't even write it right. P2 times T1. Putting stuff into your calculator is going to be super important to do that correctly here. So let's make sure we can read our list here carefully and put them in. So P1 is going to be 0.892 atmospheres times V1 is 6.35 liters and T2 is 293 Kelvin. Okay, so we got that right. You laugh, but it's really easy to mix them up, okay? P2 is going to be 1.05 atmospheres, and then T1 is 328 Kelvin. If you look, Kelvin and Kelvin cancel out, atmospheres and atmospheres cancel, so we have liters here. When I put this into my calculator, I would strongly encourage you to parenthesize these because otherwise you could potentially screw up order of operations. And when it's all said and done, your V2 should be 4.82 liters. Now we talked at the very beginning of this how our conditions indicate that the volume should go down. And if you look, it went from 6.35 down to 4.82. So just be very careful as you go through these. There are so many letters that kind of sound the same with numbers that are kind of the same. And you just have to be very careful. If you have any questions, let me know. Otherwise, good luck on your homework.